dói go bhar se le éisteartlam. There we go. Right. So, and here we're in here the radiaste and you so in do some oxygen ionization. Can you go to the being with the word so to the any idea? And remember, okay? Any idea? Adam? Ionization. Right, so certain scenarios Adu, a Kali, Modina, Electron. Okay? Right, these were close, but it's way off. Right, anyway. Right, so ionizing is which you go need, right? How can they relate to happen, right? I'll atoms, right? Exactly like that. Here, what's the like 80% that you're not going to do? No. 20% oxygen, 80% hydrogen. Okay? So the really animal hydrogen figures oxygen. 20% is oxygen, 80% is hydrogen. Okay? So something that in deep sea diving is pure oxygen. Not what you over oxygen therapy. So they just put places that it's with pure oxygen. Literally animals have 20% oxygen. Right? Now, we just said oxygen is the molecules and so when you hydrogen is one. So there's the atom one that proton away, neutron away, like it's the orbital hydrogen electron away. Yes? Okay, so it's in the hydrogen. Now, make this an oxygen, 20% oxygen. So of course the oxygen charge has from 8 into 16. Okay, so the arc proton, arc neutron, and then the orbital hydrogen or electron, right? Now, right? Now switch it in the quadrillions the molecules, atoms in the that we can see, right? And I wrote down to that. So, if one of those gains an electron or loses an electron, it's ion, and that's why it's a little bit from in. So, why the other in this is no ion, no ion, add the electron. Because you can measure this, yeah, when it gains or loses an electron. Right. Now, so this thing, so the ionization bunny here and how to decide the Geiger Muller tube. Now obviously the Shaw and you need Geiger Muller, if I use the Geiger Muller tube. Okay, so device it on to measure the count of radiation. Okay, so how do you measure an account of radiation? How do you measure radiation? Right? So chain radiation funny mechanics. So in short, it is Casualty diagram. So you need to be able to sketch and name the labels. So the syllable. Okay? Now make it to could you an ammeter I guess every home. Now every means the count type the display that keeps changing that and should change counts at all. Okay? Gas argon we log through so under very low pressure. The anode of it I guess the cathode. So the outer part of the cathode ray tube is the cathode. Shaw and anode is the funny about easy to go. Now I think we will come stage on the one ton open the 1 ton which is on but check them out, cut them out. Definitely Geiger Muller tube or go just come with plastic cost that shop. No all connected because you can't break meter nor the which is not really the vehicle anyway. But really it's one in shop, it's a sealed vacuum. The short sealed vacuum are like gas argon. It's a line gas, argon gas, right? Now because of these under low pressure, right? Anode, cathode. Now usually anode is always connected to the positive or negative. What do you do? Positive cathode to the negative, right? Now chain radiation funnel candy micra I guess the chassis gas argon at that we log through. So it's not under high pressure, so therefore log, that means all the atoms are free to move it. They're free to move it, right? Now, Ainion sé rentin adu argon is so it ionizes. So when something is ionized, could you harlan atom, kailisha, no a electron. Okay? Right. So chain right there. So mark it as a reducing the new bigger molecule device journal I guess how much the radioactive source and naculus partially compass. Right. So let's continue radioactive source and naculum bigger molecule. As a giraffe planet shot. Right? So the radiation that's released from the decay of the source was suicide freezing argon gas. As the shaft freezing argon gas, just as Harley, is it ionizes the argon gas. Right? Now, so there's the answer. So anion she rent in the adu argon so it ionizes the argon gas. Okay? Rod again in Jarifa argon. So it produces positive argon gas. So that means Tasha Kalu is losing electrons. If it's positively charged, it's losing that Kalu electrons. Does that make sense? If it's negatively charged, it's gaining electrons. Right? So rather than in Jarifa argon against electron or what Jews locked Jews to bottom. Now, Carter le Lewis an electron go more syringe. So it is syringe electra and like it at a gargon in it stranded. So it is the shock connected with the battery source, and it produces a speed on the electrons, right? So Carter le Lewis an electron go more syringe electra and like it at a gargon in it stranded. So again in Chechan a chellu in so it produces more ions against electron say embro boilu free adu ele argon. So what the Harlan check? Positive to coordinates at the reverse if we show you have your positive and negative power source at the reverse. What is going to Harlan check is in the radioactive source surface of the tube. It ionizes the argon gas, making it positive, and then what the Harlan shells and the atoms that are positively charged, this is both with more speed and they produce even more. So what they call it that cause a chain reaction. So what we call an avalanche of positive ions, right? So it creates an avalanche. So right Gamtar mine, so an avalanche of electrons as fission, so it produces loads and loads of electrons. Okay? So it keeps producing, so it's gaining these more electrons. Now, Strahan, so these and Strahan electrons and anode, so these switching as which leakage these argon gas and shot, they touch the anode and shot, so boiling the anode, I get strapping via through the circuit chakra. So the external circuit we can show is at the top, because also switches in us that the argon gas is this tube, produces an avalanche of electrons as they flow and they connect to the anode. Now when an avalanche of electrons in the anode, it produces a pulse, frees the system. And this pulse then is your counter radiation. And that's what it's related to. Okay? And it keeps producing pulse after pulse, or avalanche after avalanche of electrons as it comes to compass in the radiations. Okay? Now, through an electron and anode, it is traveling via, so via is a pulse, through here to circuit chakra. Now, Fraser lean the reaction a horu, so you can digitize it, or any hard electrona, or knows any hard scaly head, no rate meter. So we use a rate meter. So you can count how many counts of avalanches per minute, per second, per second. So Cochran and Journal rate meter set as on 100 seconds you add the constant speed avalanche of electrons. That's how you're arguing. Do you see the upper centers? Fairly straightforward. So these you give a diagram hold them. And when you take your diagram and check, so in the radioactive source is just a tube to argon gas, it ionizes the argon gas, it produces more electrons, and then it produces an avalanche of electrons. So the avalanche are main electrons freed in an anode against the inside field nectar feed the circuit and hence the Galvin Shin the Horgugine Kodu or ADR the constant state field the avalanche main electron facade producer. And that's how the written is. Which is okay. Okay? Now show solid state rate meter, so this is a different one. Okay? Now, to radiate the later and breathe our solid state. Now, Concha, it's open, it's a gas, argon gas tube. Concha is a solid state. So doi opens this up. It's A can shot and a PN cool leafer. Now, the least PN is positive negative. Now, near so example like you see the range of PN cool leafer, there's the electricity Janssen, you should know exactly what it is, right? But near the chapters in Janssen. So rather than shot is two different substances, positively charged and negatively charged substance, which we call a semiconductor. Why is your a semiconductor river? Why is your popular semiconductor? Yes. So electronics, the semiconductor, everything's made from semiconductor. All electronic parts are made from semiconductor. And rather than semiconductors, there's two different chemicals mixed together. One is positively charged, one is negatively charged, and then one produces electrons, one creates holes that picks up the electrons. Okay. Now, cool leafer against cool leafer is forward biased and reverse biased. So, race person mechanical mode junior start. There's a diode of it, which is a semiconductor. It can flow in one direction only, and then when it's a reverse bias, it doesn't allow those directions to flow. So, race is in calculation. Now, so really rather than shot, the amplifier, so you have a amplifier gram here from solid state detector job. So rud the engine shell, I say on the PN cool leafer, I say nascale here, are no scalar, no rate meter more hampler, no well in radiac and shishal EG here. Now, this is what we call the depletion rate. It doesn't make no sense to use which equal the chapter jump on so really electricity. But is the why we may be even as person not going to make any, not going to make any sense. So I'll just read through it and then I'll be back to G, back to needing knowledge and the electricity, which I add the some solid state. Or see, I'll be keeping an ear out, get my key, who picks up, and you can calculate on solid state and how it works, right? Now, so another one radiate and shishal EG, that's the depletion layer through which our GSN electron pull and shut. Just a quick definition of depletion layer. There is the yes substance of it, it's positively charged and negatively charged. So the sun is going to have an excess of electrons. The T1 there is going to have an excess of holes, what we call layer poly, right? So what the Harlan said is the depletion layer then is the current is in yes substance in the kit. There's a current flow of each. When the current flow of each, what happens is the electrons will move into the positive holes and the positive holes will move into the electrons. What the Harlan said is there's a certain amount of a layer between the two substances where all the electrons will fill the holes. Okay, and there's layers at a certain voltage. Now, if you exceed the voltage, it'll the amount depletion layer and the flow. But at a certain voltage, usually 0.3 volts, the depletion layer 0.3 to 0.7 volts, there's a depletion layer where it will not allow current to flow through the circuit. Because all the electrons fill up the holes and there's no movement. And usually that's the layer. Probably not making any sense to use, but at least Mahaja, to my initial look, it'll make more sense. Okay? Now, solution the ampli loctation trust and shishal EG for each ampere and voltage on this through each of BX so it produces a pulse rate. And then this is amplified back to the detector as if the David in the pulse is a lead. Okay? So that's your solid state detector. Okay? Now, the minute radioisotopes. Right, so we back to G, that's this old job. So we back to G, so we should jump again. Rummage in the leak, and we can just in the leak. Should we jump in the room? Yeah. Rummage activity, radioactive log, radioactive behavior, just so that before you go half-life. But anyway, so we treat radioisotope a bit. So, emu makine so portakalia bucket the isotope gas til taha well lighting colon is fiji even the well ekal only get a top to the mark. So these connection of the medicine. The just the heart is that up to the mark. Therapy is tishke marian and red kala alcha no kala squanchula. Unrea they are via so we reach the sterilized food. for example, we said radioisotope, we said it's radio gamma gain, we said humpy a stereo. So, I don't know, what those of you out, Bobby, so all that, I don't know what Jennifer is arguing with what one was, but the Mobby, when it's coming to go in starlight, or actually that it was in UV light. So it is going to UV light or the be starlight, and that's really isotopes which are more. So starlight food. Reality radio gniwa, which is a radioisotope of Gursilace, agus Taliata on Gluchat substance a real and down the bio. Carbon dating reached the radio E sample Chandeliata, LMA of Gniwiata and isotope carbon uncle. So these we can use carbon dating to find out KPs to put on. Okay, and it is all about detecting the amount of isotopes. Okay, and then it's a chance skull. This is your yet on two the shekel, so thickness of anything. On fair keiko line is at so high a shekel, I guess on shekel and armshoe, I guess on air element near the whole part capture. So these in chance skull machines more that is that do so like to machine parts you get to tasha go part need use of cogs we use it for the I guess the can journal shen no breheli that she is smoke detectors. Okay, so these how does all smoke detectors work? So these particles touch just as Jahan, at least it's the isotope of the particle touch Jahan, and therefore it's in the alarm. Okay, now change to nucleus radioactivity. So this is radioactivity activity, right? So nucleus radioactivity. So so activity substance radioactivity shen and lean nucleus in substance shen and metals a second. So it's the amount that decays per second of that substance. Okay? Now, adding in it SI degree reactor. Okay, so what's the SI unit of activity? Is the becquerel. Okay, so in the SDM becquerel and planet degree reactor. Okay, now so one becquerel is heme gene kilos a second. So it's one radioactivity or G kilo in Merlin. Reaction of it. Okay. Passing yield G kilo is a R box. Nothing just on one becquerel is one. G kilo method. Yeah, that's it. That. So it's just easy short. Anyway, substance gain per second, so it's E method that. G kilo C method, yes, money. Right? Now Clay and Meha radioactive, so the radioactivity radioactive decay. Okay, so the law of radioactive decay in the lean nucleus attack mass a second, i.e. and they react a go gira which a lean nucleus gan mass. That's the law of radioactivity decay, radioactive decay. Okay, so a lean nucleus attack mass a second, a go gira, so it's directly proportional less than lean nucleus gamma. So it's the number of nucleus that's not decayed. Okay? Now, so i.e. can retimehe a gore gira a radioactive gamma, so can retimehe causing a lambda maybe ta so lambda and parasha mehe. I know we submit lambda from the wavelength. It's also used for radioactive decay. Greek alphabet is limited. It's kanji the goose in the roti. Let's check it. Okay? Unfortunately, so makes it a wee bit confusing, but at least you will get used to it. So lambda and cha is the decay constant. Okay? So mark this in the roti of nilla jarna alpha beta agus gamma. Can we decay differently yahan? We half-life differently yahan than it. Pasta yagi carbon quickly 27.7 years and so on, right? Now the least that's your decay constant. Is people thought the lock and check to decay. I guess the least I never add to a type of mention obviously is F. Now the least had the parashama, so what is the decay constant? Now in time for lambda. So a lean lambda in Sankotomiak, so retimehe equals lambda n a total in parashamahe. It's in any decide in parashamahe no and it's a second. It's per second. So it's 1 over T thing. So it's 1 over T. So it's per second. So your decay constant is per second. Okay? Now, can you tell Jeffrey half-life the isotope radioactive? So what does the half-life of an isotope mean? So these Jeffrey is T to the half. That's what we call the half-life. So these the isotope radioactive shin and tam of hoga cheek with G dagan me or le na adu a type of me. So that half of a D. So isotope shin and tam of hoga cheek with G dagan me, so that the atoms that haven't decayed, that have them have decayed. That makes sense. Okay, it's the amount of time it takes for the atoms that haven't decayed to decay by half. Okay, so sin calculation. So Kajiga Dagan me or Ledna Nadu at a gang me. Okay? Now, so Leslie Dule, we do give Sun the Tama Hogan say upon and Greenwert a lady Quillia. Okay, so by half. Okay, and there's your chart. Now, that's a decay chart for the substance to be. Okay, so rest your time. So when you half, it will reduce by half of the number of the primes of equal larger than etc. Okay, so this is the number of atoms into decay. Okay, so it will be by half. So NO is the number of atoms on decay, so it's in N0. So like the vignette plus the plutonium, yeah, you have to not always using you or something that has been artificially produced in the lab, then it would be a full, which again 0. Now, it depends on energy position at the mass and how it decays by time. So nil left, obviously, after after one decay, half life, there's a left out. Then there's a cat 1 8, 160, 1 over 32, 1 over 64, 1 over 128, and so on, so on, so on. Okay? Will continue to decay forever. Yeah, but it's going to be 0.0000, right? And go on and on and on. Okay? So, new rise of here region, new rise of here region x just gets smaller and smaller and smaller and smaller. Which is okay. Okay? Now, this we all go along the function radio niwa a go there gene like a lean nucleus gamma. But usually if something's directly curved, proportional is usually a straight line through the origin. Now, yes, that's what I have the wrong PG shot. It was always a straight line. I'll wait for the shot. This is just a curved line. Now, so Larry should not have a hogashi on and clear to later feel yet. Okay? Now, so make the sample shot. So the activity was 200. After half-life there's a decay. After second half-life there's a quicker. A third half-life is 25, 12.5, and it keeps half and half and half. Okay? Right. So Jane Beale at the Levy of this entire semester. So what is the relationship between the half-life and the decay constant, the isotope rate of Niwa? So raised to the half equals the natural log of 2 over lambda. Okay, so it's in the formula. At least there's some space in the log, in the lower table. Now, obviously, natural log of 2 is 0.693. Because you understand the half-life, natural log 2 through equals 0.693, it's come lambda. So it's in the formula from the use as in when you fix this earlier. Okay? Now, and that's the end of chapter reading. So reading your question is a 30.2 unit. So wrong and one and said the image when a free shoulder, the mold, which was that's in the research slide, which is nothing to know. These when a free mold that there's in public description and why that's wrong. So model chip is on it. What's in down here? Oh, homes in the upper name, I hope it's wrong. No? Oh, when you live in down there, right? You were to see it, the city operation nurse. Does he need to? Yeah, easy peasy. Yeah, the handy one. Right, well, does it not that? I don't think you went down that. These two look really bad. Geophysics, that's your issues. I think you have those. Can you go past the wall last night? Any handy gas in there, yeah? Yeah. No switch for you, very good. No switch in you. Nah, I don't. Would you check that? That's happened, was really good faster. Huh? Right. So you can chat. I was just going to get the big early and go in this because after the being fun you want. I was just fun you whatever. So just more. Some chemistry in this battery, but that's the only chemistry that we do. Now, so make the case you right? Right, so just the graph shows radioactivity of radioactive isotope plotted against time. From the graph find the half-life of the isotope. Right, so some case, so the half-life is 50, so go on 50 sheets within 10 seconds. So what's the half-life? So big box of the solution here, so the sheets that you quick, go on is the sheets, is go on 1, 2, 3. So this is time in seconds, so 3. So break it 3 seconds. So Darley condition. Does that make sense, Steve? Yeah. Listen alright now, Adam. 3 seconds. Now Darley shows a graph of number of undecayed atoms of radioactive isotope plotted against time. From the graph find the half-life of the isotope. So raised on top, it's 4 by 10 to the power of 20. Okay, so really more. So the sheet step value, we equate to the half-life, so contrasting the sheet. Now the time is in minutes. So you know to actually as a 10 minutes, 1 minute. So really cool information. Because I'm a server in charge, this should be 30.2 4 minutes. So everything is a minute then obviously. So that I can envision relation excuse down below, so 1, 2, 3, 4. So many also there. So should care H A sharp or J. That's 10 minutes. So just constant chart position. I take it it's the same 10 minutes, so it's a 4 minute. It's a 4 minute decay. So okay, 4 minute half-life. Right, let's give it a see. The half-life of a certain radioactive isotope is 3 years. What fraction of the isotope remains undecayed after 3 years? So Jimmy the factor needs either Adam, come on. If we're full at 0, after 3 years we decay by half. So what's left? Half is undecayed. Yeah. So the left is undecayed. Now, Steve make this need 6 years, 1 quarter, and then 9 years is 1/8. Yeah, so precisely. So half, a quarter is 1/8. Is that you can it? Yeah, right, you can have it. The half-life of a certain radioactive isotope is 10 years. What fraction remains undecayed after 40 years? So that means you have read 4. Now, Deutsch Verla saw it go through 4 half-lives. 10 years, 40 years, that's 4 half-lives. So 2 to the power of 4 is 8. So dog to dog half to dog arc back. Dog to data packet 1, 16. Because you've got 2 to the power of 4, 16, so it's 1 over 16. Just go if it's 4. No, if it's 4, so it's just 2 to the power of 4. It's 1 over 2 to the power of n. So if n is your number of half-lives. So it's going to go in machine. So if it's so mosquito has it after no half-life, it's 1 over 2 to the power of 0. There's no half-lives, so that anything to the power of 0 is 1, so that there's 1 full time, right? Now 1 over 2 to the power of 1, that's after 1 half-life, it's half. After 2 half-lives, 2 squared is a quarter. After 3 half-lives, it's 1/8. It's far easier 1 over 2 to the power of n. And you haven't seen the text though, but at least it's just a quick way of working it. After 4 half-lives, 2 to the power of 4 is 1/16 remaining. So from 1/16 of undecayed fraction. Does that make sense? Okay? And so on, so on, so on. Now, so multiplication of the Kehrenchen, what fraction has decayed in this time? So So Jimmy, that's the kid is 15 over 16, that's the kid. So there's 1/16 remaining on the kid. You get your, there's 1/16 on the kid, so there's 15 over 16 the kid. Okay, right, kid Canella. Just super quick. The half-life for certain isotope is 20 minutes. So how many half-lives in 5 hours? So 20 minutes to answer 5 hours, that's 15. Okay? Yeah, see for quick yeah. So 15, so it's 1 over 2 to the power of 15. Does that make sense? Of half-lives. So how many half-lives in 5 hours? 15. What fraction remains undecayed after 3 hours? So 3 hours and C to C, that's 9. So 1 over 2 to the power of 9. Robert, does you know? Right, so you can do this without policy in it. It's 1 over 2 to the power of 2 to the power of 9. So dot for dot k half, for dot r, for dot c, for dot r dot, for dot s k half, for dot k to the r, for dot 2 5 6, for dot 5 12, 1 over 5 over 10. Okay? So go. Right. So it's 1 over 5 squared 12. Right, so what fraction has decayed in 40 minutes? So that's 3 half-lives. So in the 40 minutes, so 3 quarters have decayed. Big minutes, so it's 3 quarters. That's 1 quarter remaining after 3 half-lives. So 3 quarters have decayed. Just be E between my plus. Okay? Castilla, what fraction remains undecayed after n half-life? So what fraction remains undecayed? So it's 1 minus 1 over 2 to the power of 10. So this is why they given this. So it's 1, it's not 1 over 2 to the power of n, it's 1 minus, no, it is, it's 1 over 2 to the power of n. It's 1 over 2 to the power of n, not 1 minus. That's the amount that has decayed. Okay, it's 1 over 2 to the power of n. Okay, is it okay, listen? Okay. So you know, what's the no, right, okay. Right, so kiss the shape. A radioactive isotope has a half-life of 120 seconds, calculate the decay constant. Right, so your decay constant. So in formula, asking for your decay constant. T to the power of half. So T half is equal to log of 2 is gone lambda. What is lambda? The lambda can you work in? Yeah, lambda is what we're looking for. Right. So J how many generation in that? So at least gets the shape calculate radioactive to half for 120 seconds. So at least test go T half is 120 seconds. Which is the generation? Yeah, so 120 seconds. Lambda equals natural log of 2, so the lambda equal to natural log of 2 is going to k to p. To get your solution calculator. Natural log of 2 is going to k to p, so to figure it out. 5.7. We just do correct the 2 decimal place, 78 by 10 to the power of seconds. Is it seconds or per second? Per second. So we could have it's the second. So it's s to the minus 1.
Jumping up on Shinshin, yes, I had the Mohanish Lahigam Leah.
Anyway, Bishati is circling in the background. Geishers right, Kira, Kila, Exania. Right, so I'm still up our Kishni 30.2. We'll brew possum.